This is lecture 21. In the last couple of lectures, we talked about injuries and healing. In this lecture, the last one of this block, we'll talk about active and reactive hyperemia, mostly active, meaning the skeletal muscle pump. What causes the pump during a weightlifting session? We just have these two topics for today, reactive hyperemia and active hyperemia, the latter being the pump. So hyperemia is swelling of a kind, but it's not the same kind as the injuries here. The swelling here is explained by vasculature being made more permeable by things like bradykinins and complement proteins and platelet activating factor, tumor necrosis factor, vascular endothelial growth factor, and so on. Lots of things. And then proteins start leaking out of the vessels because they're porous and into the surrounding tissues, and then water follows. Water follows those proteins. So that's the swelling here. But this stuff is differently swollen. And I'm not talking about hypertrophy, swollen, like not that. I mean, the muscle temporarily inflates during exercise and then it deflates after. The pump that we get during exercise, that's a form of hyperemia, which is just excess blood going to some tissue or organ, in this case, skeletal muscle. So let's talk about reactive hyperemia first. In skeletal muscle, still, reactive hyperemia means you limit blood flow temporarily, you restrict it, and then after a time, you stop restricting it, and it'll rebound or react with an excess. That's reactive hyperemia. So in this study, they looked at 14 subjects. There was some men, some women, some young, some old, some healthy. There were healthy volunteers, and then some were patients with potential perfusion abnormalities. And they put a cuff on them, inflated it, and induced 5 minutes of ischemia. And then they released the pressure and watched what happened. They measured what happened. And here we're looking at the healthy volunteers only and the measurements for four different lower leg muscles and then a global perfusion measurement labeled leg. And you see significant increases in perfusion from pre-ischemia, that's the rest column, to post-ischemia, that's the reactive hyperemia column. So after 5 minutes of ischemia, all values are significantly increased in all of the muscles. So if you occlude blood flow, it will be followed with a surge, low tide and then high tide. So what's causing it is the release of a bunch of metabolites. We'll talk about which substances are doing it in just a minute. But for now, lots of stuff gets released. And some of that lots serves as vasodilatory agents, vasodilating agents. And maybe there are differences in hyperemia between muscle groups and between fiber type. So the metabolic byproducts in like a type 1 muscle and a type 2 muscle, these are going to be really different. Type 2 muscles, those have faster ATP consumption, so there'll be more lactate, more hydrogen ion accumulation. And that can affect by itself, that could affect um, the environment that's being released to the blood. So in the muscles we're looking at here, it's the soleus, which has more type ones, and the gastroc, which has more type twos, and so there may be differences in the muscle fiber type, explaining hyperemia differences. And this isn't just a phenomenon of skeletal muscle either. It exists all over the place. The liver, the kidney, the intestines, the skin. Wherever there's a buildup of vasodilating metabolites, you'll get an excess of blood following occlusion. And then throughout the occlusion, the metabolic environment will change. The ratio of aerobic to anaerobic, you'll become more and more anaerobic as the occlusion is maintained. And so in the graph on the left, you can see the rise in NADH, that electron donating compound. NADH excess indicates more reliance on anaerobic metabolism. Now on the right, that's the red blood cell velocity that's reduced during occlusion and then it rebounds during reactive hyperemia. And then here we're looking at different presentations of hyperemia based on different durations of occlusion. So 60 seconds of occlusion, 90 seconds of occlusion, 120 seconds of occlusion, and so on. Each color is a different duration. And then we're looking at the hyperemia response of each over time. And then given that the phenomenon it happens in so many different vascular beds, you have muscle and kidney and skin and so on, and there are different ways to induce it and then different presentations. Once it's induced, it's hard to say exactly what's causing it. Unless what you're saying is sort of vague and inclusive of lots of options. You just have to make room for variation in the different presentations. So summarizing the findings of reactive hyperemia, in the left paragraph, it just describes shorter and longer occlusions that correspond to smaller and larger hyperemic responses. And then in the right paragraph, there's a number of mechanisms proposed. Again, I'll talk about this in just a second. But getting into active hyperemia, this is an exertional increase in blood supply, which that's the pump, that's the like weight room pump. Skeletal muscle pump kind of means something else, but the pump you get when you're doing resistance training. And the biggest contributor of hyperemia in exercising muscle, it's vasodilation. It's blood vessels opening up to send more blood to those muscles. And what really determines blood flow is metabolism. So, like during a back massage, the masseuse's hands are experiencing greater increases in blood flow than the client's back. So here we're looking at Ainsworth's compendium, and like so, if you're hunting a large game and dragging their carcasses, that has a MET value, MET, metabolic equivalent of the task, a MET value of 11.3, which means it's 11.3 times your resting metabolic rate. And if you're scuba diving as a frogman, that's 12 times your resting metabolic rate. Um, if you're in the forest, right, chopping down trees at 51 axe blows per minute, that's 17.5 times your resting metabolism. So, like, the point is that metabolism increases a lot. Like, no matter what activity you're doing, if you're doing any activity, you'll see your metabolism increasing. The compendium goes on for pages and pages like this, just bizarre activities, and then the corresponding metabolic cost of them, which you have to take with a grain of at least salt, if not something stronger. So that's it. That's metabolism determining the blood flow. And then the blood flow, the increase in red, blood cell flux, that's for the individual muscle fibers that are working. Blood doesn't just get hosed onto a whole tissue. The capillary beds surrounding individual fibers are where the blood is going, but it's only the working fibers with metabolism that need support that are causing this hyperemia. But those fibers, the active fibers, might be living alongside fibers that aren't firing at all. They might be living alongside some high threshold fibers that aren't actually active. So how do you get the blood where it needs to go? How do you direct it to the appropriate capillary beds? Let's begin with the limitation of capillaries. They don't have smooth muscle. Capillaries don't have smooth muscle. So they can't alter their diameter. They have to rely on the upstream arterioles to do the work of dilating and constricting. Uh, and so they just inform those arterial networks where to do the dilating. Um, so out of exercising muscles, lots of stuff gets released. Metabolism has lots of metabolites. And so as you exercise, there will be hydrogen ions and lactate and adenosine and prostaglandins, lots of informants for the vasculature to take note of. And then, like accordingly, upstream from where all of that stuff is released, that's where you see the vasodilation. The increase in blood flow from vasodilation, this takes about a second. I mean, about a second after the initiation of exercise, you start seeing increases in blood flow. But the muscles, the cells, those fibers, the individual muscle cells, those are really long, generally longer than the capillary beds. And they need to be perfused throughout their length. So they tend to have multiple different beds supplying the blood, which means they're supplied by capillary beds that come from different 4A arterial branches. And what that means is that skeletal muscle regulates its own perfusion. It doesn't just absorb stuff from the capillaries, it releases stuff to them too. And then that stuff uses the capillaries as the communication medium um, to inform the upstream arterioles. Okay, a summary of the pump. Metabolism is what determines blood flow. When a muscle fiber contracts, that's a metabolic activity. The substrates and products of that metabolism include lots of vasoactive molecules. And those molecules diffuse into the blood and that provides information about the internal metabolism of that cell, which informs the circulatory system to provide more blood, um, through which more, metabolic substrates will be provided, the reason the blood is needed. And uh, most of this increase in blood will be through vasodilation. But size principle makes sure that you recruit your motor units in an all or none fashion in a specific order, which means during muscle contraction, there will be some fibers that are active, and almost certainly there are others that are inactive. And the fibers in a single motor unit are going to be distributed throughout the whole muscle, unless there are pathologies involved. Those individual fibers will not be grouped together in neighborly cul-de-sacs. They'll be distributed throughout the muscle, and those well-scattered muscle cells receive their nutrition through capillaries, which don't have smooth muscle, so they lack the ability to adjust their volume. Diameter adjustments have to be done upstream. But muscle fibers tend to be longer than the capillaries supplying them. So they have multiple suppliers, and those suppliers can come from different upstream branches. And not all of those upstream arterioles come from the same parent. So there's this vast arterial network supplying a single motor unit. And um, the muscle fibers in that motor unit supply the capillaries with a chemical information. And red blood cells and endothelial cells, they're probably secreting some additional stuff. Red blood cells can release ATP when pH and O2 are low. And between those chemicals and the increased intravascular pressure and shear stress in the upstream arterioles and the mechanical contraction itself, compress the vasculature, open the vasculature, compress it, open it, occlude blood, release blood. Plenty of information is there to guide the circulation. And the capillaries, they do a decent job of directing the upstream traffic, conducting blood to the specific fibers that need it, and preventing the overperfusion of the inactive fibers. But you're still going to find yourself overperfused by a lot. Um, and that's your pump, right? That's otherwise known as active hyperemia. And in the next block, we'll talk about how using local hypoxia to promote hyperemia can also promote anabolic agents and hypertrophy. But that's it for now. Here are the questions from this lecture, and this is the last of the content for block 2. In block 3, we'll get into hormones, enzymes, and the mechanisms of hypertrophy.